You're about to watch an extract from one of my live TikTok lessons. This one's focused on energy. So if you find it useful, make sure to hit that like button and tell me what physics topics you'd like me to cover next. Now enjoy. I am way too overdressed for this. We'll start with the one that I saw the most in there, which was called kinetic. So if you've got kinetic energy, okay? Kinetic energy is what we call moving energy. Anything that's moving has got kinetic energy. Now this is where some misconceptions come, because I've seen some people write in there as well about like light. Light, technically, we can think of it as energy, yes, but light energy is actually a type of kinetic because light is moving, okay? So it's a bit random that you kind of go, wait, what, light is kinetic energy? But it's moving, so we have to consider it as kinetic. Same with sound. Sound is particles bumping into each other. They're moving, so we count that as kinetic energy. Thermal energy, we can just think of as heat energy. So anything that feels warm, we're dealing with thermal energy. Gravitational, we'll call it gravitational potential energy. The big misconception I see with this one is that lots of people confuse it with gravity, because it's not about gravity. It's about it being an object lifted high into the air so that gravity could act on it. Okay, that's the big difference. So if we take an example of this pen on the table, okay? This pen here is stopped by this object, okay? But it's still off the ground. If we were to measure the distance, it's probably like half a meter or something like that. But as I lift it up, okay, I'm making it move, but I'm transferring energy from me to this pen because I'm lifting it up and up and up, okay? The more I move it up higher, the more gravitational potential energy it has. Okay, so the higher it goes, the more GPE it's going to have. If I let go of it, the force of gravity is going to act down on it, pushing it downwards. Okay, so that's the force acting on it, and we can see it drop down. Now, as it's dropping, it loses the GPE because it's not at the same height anymore. We're going from creating a situation where it's got GPE, it's moving higher and higher and higher, gaining your GPE, and then it loses GPE by moving downwards. Okay, it's really big. It's actually really big in your exams normally. You'll see lots of the physics papers will talk about the kinetic energy equation and the GPE equation, because we're looking at, you know, the things that come down to the energy in GPE is about, you know, how heavy your object is, how high it's going up. They're kind of the relevant points about your GPE, and then the gravitational field strength does come into act on it there. Okay, gravity is only one part of that equation. There's three total parts: your mass, the height, and the gravity on that planet. Because if we were to look at GPE in a different planet for the same object, the amount of gravitational force there is going to be completely different. So if you think about like Earth versus the moon, the Earth's gravitational field strength is like way stronger than the moon's. Or we're at 10 meters per second, whereas they're 1.6 meters per second. So the gravity on our planet is so much stronger, it would pull you down a lot quicker. 9.8, yeah it is, but a lot of the time you're allowed to round them to 10, so that's what we tend to say. So after Now, what I want people to think about when it comes to chemical energy is food and batteries.
B8-2-res. Batteries. Batteries.
Ironically, we were talking about molecules earlier, so if you think about like those carbons bonded with hydrogens, bonded with oxygens, all of that stuff, that is the energy I'm talking about. It's locked up inside the molecule. Two different, very different styles of chemical energy, but they're still both chemical energies. Electrostatic, okay? Electrostatic, if we think about what we were talking about earlier with your ionic substances, you've got a positive charge, you've got a negative charge, they're attracted towards each other. That's electrostatic attraction. We're looking at those opposite charges pulling. Elastic potential. If you've ever done archery, you'll know what I mean about elastic potential. You're taking the idea of moving and that band, that bow back, okay? You're pulling back on it, you're giving it energy. So you're actually transferring energy from the cells inside in your body, inside there, chemical energy. You're pulling it back, transferring energy into that elastic, okay? And you'll know that it's got energy because if you were trying to hold that for a really long time, you can feel it pulling away from you. It wants to move. And that's how you know that it has energy. So you're pulling and pulling and pulling on it. You can feel that pull, and it requires energy from you to keep it there. But when you let go of it, boom, boom, it starts moving. It transfers it to kinetic energy. But elastic potential is that idea of like if you have an elastic band and you pull it and it's got like that spring on it, boom, boom, it's going to move. That's elastic potential.
You get me? Boom.
So nuclear energy, this is to do with the energy inside in a single atom. So it's actually inside in the nucleus. So I know when we think of nuclear energy, we think of nuclear power plants, but you also have to think about nuclear bombs and how the energy are working there. So what's actually happening inside in the nucleus of an atom, you have your protons, you've got your neutrons. If you destabilize it in some sort of way, then your atom wants to rejig itself and become a different element, or it might want to lose a neutron, it might want to fire something out, it might be an alpha particle, a beta particle, could end up giving out gamma radiation. Okay, so when we're looking at nuclear energy, we're looking at something inside the nucleus of the atom releasing that energy out. And that's what's happening in your nuclear power stations and what's happening in a nuclear bomb. That's the kind of big thing, okay? So nuclear energy is to do with the nucleus of your atom. So someone put in the last one as well. The last one that we had was magnetic. So again, we're used to seeing how magnets behave. We know that magnets have that opposite charge as well, at the opposite poles, a north side and a south side. If you've got north and south together, they're going to pull. If you've got north and north, they're going to repel. If you've got south and south, they're going to repel. That's the key, okay? So we're dealing with looking at those opposite poles, either attracting or similar poles repelling, okay? It itself is a force, right? That's your kind of 8 energy stores. One really important aspect to it is about the actual mass of the moon. So anything that has mass technically has a pull towards it. So that's why the sun has got a huge mass and it's pulling all of us around it in orbital. The best way I've ever seen gravity described, if you put someone really heavy into the middle of that trampoline, where they are is going to go down. You start to see this kind of area pushing in towards it. Now imagine that you had marbles, right? And you flung a marble around me. Well, it's going to orbit around me, but eventually it's going to move in towards me as well. That's what's kind of happening with your gravity. It's the idea that you're moving towards a big center of mass. Great question. It is 100%. So when you think about burning, what you're doing is you're releasing the energy from whatever you're burning. So if we think like we're burning wood, wood is actually mostly carbon, hydrogens, oxygens bonded in some sort of way. When you're burning them, you're breaking those bonds between the carbons, hydrogens, oxygens, releasing energy and making new molecules.